So yeah, I sort of rushed through an example of this last time. And once I started it, I had to finish it. We don't do half jobs.
Right?
Huh? What? Yeah, that's just, I couldn't. And it's one of those problems where, like, if you stop halfway and then it's like you get totally confused next time. So
it's unacceptable.
yeah. So we sort of rushed through an example. I believe I told you guys what an ordinary point was, right?
You said you're gonna go, like, we're gonna go back later to.
Really? I did.
Yeah. Let's check this with you.
This definition. We're looking at second order differential equations. We're looking at the homogeneous one, but this also applies to non-homogeneous ones. So let me make that more general. Focus in this class is homogeneous, but whatever. A point x equals x naught for which p of x naught is not 0 is called an ordinary point. Right, these are the nice points. We don't really have to worry about them. The thing is, when you put this in standard form, you have to divide through by p, and if p is 0, that's a problem, right? So as long as it's not 0, everything is sort of fine. We don't really have to worry about it. Everything works out nice, and as long as these functions are analytic, we can find a series solution. Analytic just means we can represent them by power series. Right? So once all the functions accounted for, we can write power series to represent them. We can find a series solution. That's pretty much all we need. And when this is not 0, we're good. That's called an ordinary point. In the case where this is 0, it's called a singular point, and we'll deal with that in the next section. Is that the next section? In the 2 sections later. Okay. So we actually did an example, basically to find a series solution. So that's the end of the definition. To find a series solution centered at x equals x naught, we assume that y can be written as a power series centered at x naught, right? So the series from 0 to infinity, n equals 0 to infinity, an x minus x naught to the n. And basically we follow the consequences, right? You find the derivatives, you plug this into the differential equation, and the point of doing that was to find the coefficients a n so we could figure out what the power series was. Right? So last time we rushed through an example where we actually knew what the answer was, that was sine and cosine, and we did the series solution and we realized, oh, we ended up with the series for sine and cosine. I just want to do a couple more examples, 1, 2, 3 more examples, just to hit it home, like how this thing works, because it's really just, again, another mechanical thing. You just have to get into the groove. The problems here can get sort of long, but again, the steps are always the same. So let's go into another example. So here's our equation y double prime, xy prime minus y equals 0. Here x naught equals to 1. So here I only require that you find the first 3 terms of the series. First thing is, I want you to appreciate that our technique so far does not allow us to solve this differential equation. Right? So it's not something that, we couldn't use y equals e to the rt or anything like that to solve this. It just wouldn't work. So what we do now is we therefore assume y equals the series solution, the series an x minus 1 to the n. Because that's our x naught. Sometimes it's 0, but sometimes it's not. You have to be aware of that. So, of course, I'm not going to always write this down. You should, at some point, be able to figure out what the derivatives are without having to take the time to write them down. Just start plugging them in. But I'm just going to write them down for now. Just differentiate term by term. Now we want to plug this into the differential equation. Does anyone see a problem so far? Because there is actually one staring us in the face.
Just an X.
There is an x. Why is that a problem that there is an x?
It's not a constant.
Because we won't be able to factor this x.
You won't be able to factor? What does that mean?
Because I thought after we plug it in, we have to factor the x minus 1 is saved.
Well, factoring is not the right word. So let's say you plug this in. I'm just going to, you don't have to write this, but I'm just going to explain. I'm going to write out what we have here and show you why it's a problem. Right? So we'll go from 2 to infinity, a n minus 1, a n x to the n minus 2, minus x times the series from 1 to infinity of n a n x minus 1 to the n minus 1, minus the sum of a n x minus 1 to the n from 0 to infinity. Now do you see what the problem is? The last time we did this example, what did we do? We wanted to combine all the series, right? Which means I needed to bring this x inside. Now when this was just an x, that was easy. I just add the powers. But this is not just an x anymore. This is an x, but that's an x minus 1. Which means I can't sort of bring this in and just change the powers. It messes things up. The fact that this is an x is a problem because now I have to think of my variable as being x minus 1. Right? Now there are a couple of ways you can do this. You can think of x to be x minus 1 plus 1, right? And expand it that way. Another way, it's pretty much the same thing, but it just makes writing easier because I don't want to be writing this x minus 1 all the time. Another way is you just do a substitution. Set z equals x minus 1. Which would mean that z plus 1 is equal to x. This means I can rewrite this series. Y double prime minus z plus 1, y prime minus y equals 0. This is y double prime minus z, y prime minus y prime minus y equals 0. And then I assume y equals the series from 0 to infinity of a n z to the n. So now it looks a lot nicer. And of course I know what z is my x minus 1, so when I get the final answer in z, I just back substitute the x minus 1. But now this is going to be very similar to what we've seen before. So we plug this in. To infinity n minus 1, a n z to the n minus 2, minus z times the series of n, a n, z to the n minus 1, from 1 to infinity, minus the series of n, a n, z to the n minus 1, from 1 to infinity, minus the series from 0 to infinity of a n, z to the n, and all that is equal to 0. Now we want to start to simplify. The first one, let's just leave that for now. 2 to infinity and n minus 1. Oh, no, we don't want to leave that. All right, so remember what was step 1? Fix the powers. Fix the powers. You want them to go to n, right? So this guy, how do I change that power to n?
Plus 2. And plus 2.
Take all n's, replace them with n plus 2's, right? So that would mean this series would give me 0 to infinity of n plus 2 times n plus 1 times a n plus 2 z to the n minus. This one, when I bring the z in, it's automatically going to change, right? That's going to be n a n z to the n, because I just add the powers. This is z to the 1. To infinity. Minus this one, I'm going to have to do the shift, replace all n's with n plus 1's. So this 1 will now become a 0. N plus 1, a n plus 1, z to the n, minus this one is already at z to the n. What was step 2? Make the indexes the same. Well, the plural of indexes is. So everyone here is at 0 except this guy. So what do I have to do to get him to 0?
N minus 1. Replace n by n minus 1.
No, that would change the powers. Remember, you never do a shift to change the index.
So we have to take the first term, which is 0, and separate.
The first term is going to be 0 if I can literally just replace this with 0. No consequence, because then it wouldn't make a difference. So in this case, I didn't have to do, I'll do an example where we have to actually deal with that issue. But here we don't. Just replacing this 1 with 0 makes no difference because the first term of this series will be 0. So now I can literally combine them all into one big series starting from 0. Now we have n plus 2, n plus 1, a n plus 2, minus n a n, minus n plus 1, a n plus 1, minus a n, all of this times z to the n equals 0. Now there's 0 on this side, which means the coefficient of the series on this side should be 0. Right? So that gives us an equation. Do I have an eraser? So basically, really what's happening here is that we're equating coefficients. We're thinking of this as the series of 0 z to the n. Right? It's just 0 plus 0z plus 0z squared plus 0z cubed plus 0, etc. Right? When we equate the coefficients, it means that all the coefficients over here have to be 0 to match up to that side. Which sort of tells you what you need to do. If I gave you a function here, all you have to do is set the coefficients here equal to the coefficients there. But in the case of 0, you just set it equal to 0. This gives us that n plus 2, n plus 1, n plus 2, minus n a n, minus n plus 1, n plus 1, minus a n equals 0. Okay, and what was the next step? This is probably step 4. I'll call this settings to 0, step 3. Okay, what do we do now? What's the next thing?
So for a n plus 2.
Right, solve for the largest index. Right, so this means I'd solve for a n plus 2. This gives us n plus 1 a n plus n plus 1 a n plus 1 all over n plus 1 times n plus 2. Can I simplify that?
You cross out the n plus
Right. N plus 1 is common terms. You can factor them out and cancel. Not cancel and cross sums because that would be a blasphemy. I'm just skipping this step right
No,
back.
do that.
Yeah, you do that, you die. Okay. So this means that
How
n
bad
plus
do we die?
annihilation, ultimate annihilation. I stop reading your test and I go to the front and I write down 0. Okay. So
Wasn't there an AN2 on the top? There should be another AN.
an.
When you
Yeah, this one here I combine them.
Oh, okay.
Right, this is, I factor out a minus 1, I get minus n plus 1 an, and then when I move to the other side I get plus n. Right, there are two of them. I just factored these together. Right? These two together gave us n plus 1 an, and I moved it to the other side. So now this guy here, we had a name for this. This is called what?
The recurrence for
Recurrence relation. It's important to know what it's called because they just might ask you, find the recurrence relation.
Everything looks big down here.
Huh?
Everything looks so big down here. I'm sorry.
My allergy medication.
Alright.
I'm dying in this photo.
I understand what he said. I put a GoPro on my dog once. I watched it. The world from the view of a dog. It looks huge. Yeah, that's true.
How big was your dog in the first place?
It's like this.
Of course it's gonna be big for him.
Okay,
He's
all
like,
right.
who is this Jhevon
So
monster?
basically what this guy helps us to do is find the coefficients of what our solution should look like. Now remember, our first two guys, A0, A1, they're just themselves, right? They might be given if we had initial conditions. This would be the y of 0, this would be the y prime of 0. But everyone else, usually you'd need to use this to figure out, right? So to find A2, what do we need to do? Let's plug in n equals 0. Right? So if n equals 0, that would give me A0 plus A1 over 2. Right? So it's A0 over 2 plus A1 over 2. A3. Now to find A3, I plug in n equals 1. This gives me A1 plus A2 over 3. Right? Now remember what we said before. These guys here, we want to find everyone in terms of those guys. This is an A1, that's fine, but this is A2, we don't want A2. Everyone should be in terms of A0 and A1. That's going to allow us to separate our series into two linearly independent solutions. So it's not a big deal. All you do is you're going to replace A2 with what it was before on top. So this is just going to be A0 over 2 plus A1 over 2 all over 3, which is the same as
0 over 6.
A0 over 6 plus A1 over 6, which we're going to want to combine here. So this is 2 over 6 plus 1 over 6, that's 3 over 6, that's a half. So this is A1 over 2 plus A0 over 6. Now remember, one set of the solutions is going to have the A0 as the main guy, and one is going to have the A1 as the main guy, and so far I have 1 A0s, 2 A0s, 3 A0s. This is enough for 3 terms for the Y1. I have 1 A1, 2 A1s, 3 A1s. We're enough for 3 terms. You don't have to go any further, right? So this means our y, remember what we said, we assumed it was a series. So this is what it looks like. A0 is itself, A1 is itself, A2 is now this So I'm just going to replace it. So this is a0 over 2 z squared plus a1 over 2 z squared plus a3 is this guy. So I just replaced that one. So this is a1 over 2 z cubed plus a0 over 6 z cubed, blah, blah, blah. Basically, now what I want to do is I want to group them. Group the a1s and a0s. So a0s, what are the a0s I have? I have 1. I have z squared over 2. I have z cubed over 6, etc. Right? That's the first 3 terms of that guy. Plus a1. I have z squared over 2. Z cubed over 2. Now I have to remember, z wasn't my original variable, so I'm just going to replace these. These are all x minus 1s. So this guy here is my y1. This guy here is my y2. Okay, any questions?
My God.
What is, where you wrote step 3, what exactly is?
Step 3 is just setting this equal to 0 to get that equation. I'd like to call it a step because it is actually something you should think about, because what you do right now would depend on what's on the right side. Right? So because the right side is 0, that's why you set it to 0. If the right side was something else, you'd set them equal to something else. Right? That's the important part. Yeah.
So that's how we created on that board, where it's Z,
Mhm.
and then it's the, then when the Z is outside, how do you combine that, and how do you combine that in?
I can multiply in.
And then,
Remember, the series runs, n is what the series has the variable. So z is a constant with respect to the series. I can just multiply it in. And so when I multiply z times z to the n minus 1, I get z to the n.
does the index change or not?
No. Doing that manipulation doesn't change the index. No.
Okay.
Any other questions? Yeah. I'm not changing where the series starts counting from. I'm just multiplying the existing series by some number. So it's not going to change the index. I never asked this, but follow up. Because it's conceivable that you could be asked this. Show that y1 and y2 are linearly independent at x equals x naught. How would you do that? Find the Wronskian. Right? Or I could have also asked something like, show that they form a fundamental set of solutions at this point, or something like that, right? So how would we do it? Plug this into the Wronskian, differentiate that, plug this to differentiate that, multiply out all the polynomials, right? Like, hell no, why would we do that? Okay. I asked you specifically at the point x naught, so I'd actually evaluate that. So y1 at x naught is just y1 at, in this case, our x naught was what? 1, right? What is that? When x equals 1, what is y1?
1.
That's just 1, right? Because all these guys go to 0, but there's a 1 in front.
That took too long. That took too long.
And so our y2.
That took too long. It was like, what comes after 1?
Yeah, Vincent got jokes today. Okay, so at 1 we would have what? 0. Which means that the Wronskian of y1 and y2 evaluated at the point 1 is just going to be 1, the derivative that is 0, 0 derivative that is 0. And that would actually be 0. So that's actually a problem. So I should probably phrase this question as
Problem.
not as a problem. Like R is R y1. Oh, yeah, I can R. That is sort of strange. Anyway, let's move on. I did have an actual follow-up. Suppose I gave you this information. Suppose in addition I told you that. What would the general solution be? They're having way too much fun at 8 a.m. What is the general solution? Y equals what is this guy, the 2, in relationship to what's over there? That's right, it's A0, right? And this guy is A1. Which you mentioned last time. You just plug them in.
Right? Really? I don't see that.
I mentioned this last time when we went over 5.1.
Did you?
I did.
Let's just go back to tape. The guy's too stupid.
Okay, we got to pick up the pace because I wanted to get through a couple sections today. Let's do another example. Some of you will have some trouble getting used to this, but it's one of those things, once you get used to it, it's actually not that bad. So let's cover a couple variations. What's positive? No, this is, I assume this is -1.
Oh.
Okay, let's try to run through this example quicker. We don't have to do a substitution here because it's already at 0. X is already a nice spot. So one of the first steps you have to remember is that you're going to want to multiply in at some point. So having something like this is a bad idea. You're going to want to expand this. Right? You sort of want to expand everyone. So of course we assume, I don't want to write this all the time because I don't expect you to write it all the time. Assume y is equal to the series of an x to the n. This will give us what? This is the second derivative, so this is the series from 2 to infinity of n minus 1 an x to the n minus 2, plus this would be the series from 2 to infinity of n minus 1 an x to the n, because I multiply this x squared in, minus this would be 4 times the series from 2 to infinity of n x to the n, again because I multiply this x in, plus this 6 series an x to the n from 0 to infinity equals 0. Now what do we have to do? We have to fix the powers. So in this one I'm going to replace all n's with n plus 2's. This will give me starting at 0, n plus 2, n plus 1, n plus 2, x to n. This is already starting at n. However, the index is 2. We will not do too many things at once. So here I changed all the powers to n. Next time I'm going to want to make sure the indexes are the same. Turns out I can just replace this with 0 and there's no problem again, right? Because when n equals 0, it's dead. When n equals 1, it's dead, and then it'll start from 2. Same thing here. This one.
So for the second line, how is the first index 0 from 2?
Because I replace all n's with n plus 2's. So So remember, when we're shifting, we have to replace n. It includes all n's, including this one. That's in the index. Right? Right? So this n here, I'd replace with n plus 2. So I get n plus 2 equals 2, which means n equals 0. And so now it will start at 0. And then I have to replace this with n plus 2, this with n plus 2, this with n plus 2, this with n plus 2. Every n's everywhere, including in the index, is shifted. Okay? So that's why this 2 will shift to a 0. And this one, I force it to 0 because it's not really going to make a difference. This one I can also force to 0 because he's not going to make a difference when n equals 0. And so I can start everyone at 0. Once everyone is at 0, I can plug them into this big gigantic series. I can combine the series like we looked at last time. So I have n plus 2, n plus 1, an plus 2, plus n minus 1, an, minus 4n an, plus 6 an, x to the n equals 0. And set is equal to 0 to match up with the coefficients on that side. This gives us n plus 2, n plus 1, n plus 2, plus n minus 1, an minus 4n, an plus 6, an equals 0. And so now we are going to solve for the largest index. Which, by the way, I can probably simplify this a little bit, right? This guy is really I just want to simplify to see if anything would cancel. This is n squared minus n minus 4n, so this would be n squared minus 5n plus 6 times 8n. Right? And that guy actually factors, right?
Yes.
This would factor into
Oh,
6 and 1.
actually, 1.
Huh?
3 instead of negative 3.
Is it 3 and 2? Yes, it would have to be 3 and 2. I was hoping it would be 6 and 2. All over n plus 1, n plus 2. So nothing gets to cancel. So this guy here is the recurrence relation. So A0 and A1s are themselves A2s. We're going to use this guy, plug in n equals 0. If I plug in n equals, how many terms did I ask for here? Maybe we'll do up to the first 4 terms or something.
You didn't ask.
I didn't mention. Yeah. Anyway, A2 and 2 is when I plug in n equals 0. So this is just
Negative 6.
6. Right?
Negative 6 over 2.
Right. Negative 6A0 over 2. Negative 3A0. A3 is when I plug in n equals 1. So that would give me 1 minus 3. Minus 2, 1 minus 2 is minus 1, A1 over n equals 1, I said, so that's going to be 2 times 3. So this would probably cancel that, and we would have minus A1 over 3. A4, let's just do one more. For A4, we plug in n equals 2. So this is 2 minus 3. It's minus 1. 2 minus 2 is 0. So that's just 0. That's an interesting trend. This means that anyone who depends on A4 would actually be 0. Which means we're going to have zeros on every 4th term. We can do another one of this. But what's going to happen here? A5 is when I plug in n equals 3.
0.
Yeah, 0.
N equals 3. No, n equals 3 is going to be what?
3 minus 3 minus 3. 3 minus
3 minus 3. It's also going to be 0. And then A6 would be what? If I want to get A6, I have to plug in n equals 4, but A4 is 0. Right?
So all terms.
Every term after this is going to be 0. That's probably why I didn't mention how many terms I want. Yeah, I forgot. I write these lecture notes half asleep. You have to understand. This implies n equals 0 for all n greater than or equal to
Equal to
4.
two.
Should be n
Two,
equals 0
two,
to 2 or 4.
Two.
What are you talking about?
No, because like if you're plugging n equals 2, that's one thing, right?
Oh, wait. I was thinking of the 4th term.
You're still half asleep, boy.
Let's say 4, 6, it's 8.
Dude, I woke up at 4:30. No excuse.
2.
What time did you go to bed?
12.
Okay, so now what? We can literally write down the whole solution to this thing. Right? What is the entire solution? We don't even have this here. We know that y was a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th, etc. Right? But our a4 onwards, from this point onwards, they're all zeros. So we literally just have a cubic being the solution to this differential equation. This gives us y is equal to a0 plus a1x. a2 was 3a0. a3 was minus a1 over 3. This is the entire solution. I thought that example would be nice. Sort of freak you out. The series solution really isn't a series. Well, it sort of is, but every other term is 0. So it is often possible to get a closed form solution.
Jhevon, where did the 3 go? To the last one?
3
Last one.
should be there. That 3? Yes. And of course now if I give you initial conditions, all I have to do is plug them in here and you can find the exact cubic that will match that differential equation. Okay, let's end this section with one that's slightly harder. Which we're building up to this one, and it was actually a past final problem, so you'll see the level of series that you'll need to know. So this is from fall 2011, problem 4. We're given this series, this ODE, 3 minus x y double prime plus x squared y prime plus 1 plus x y equals 0. X naught equals 0. Find the recurrence relation. And the series solution given. They didn't phrase it exactly this way, I'm paraphrasing, but basically this is what it said. Y of 0 is minus 6, y prime of 0 is 2. So this is actually a final problem. So it looks like. So we assume y is equal to 0 to infinity, a n x to the n. This means we're going to start plugging this guy in. Remember, this guy I'm going to think of separately, 3y double prime minus xy prime. So this would give us 3, from 2 to infinity, n minus 1, a n x to the n minus 2, plus, well, minus. This is now n minus 1 because I multiplied the x in, plus. For the derivative, I'm multiplying in x squared. So this would be n a n x to the n plus 1. plus 1 times y, which is just a series from 0 to infinity of an x to the n, plus x times y, the series from 0 to infinity of an x to the n plus 1, all that equal to 0. First thing we want to do is get all the powers to be the same. So I'm going to change all n's to n plus 2's here. So this is just 3 times the series from 0 to infinity, n plus 2, n plus 1, an plus 2, x to the n. Change all n's to n plus 1's here. So this series will actually start from 1 to infinity, n plus 1 times n, an plus 1, x to the n, plus, now I'm going to have to change all n's to n minus 1 to fix this one. So this will be starting from 2 to infinity, n minus 1, an minus 1, x to the n, plus this one is fine. Plus, again, have to change all n's to n minus 1's. This is going to start at 1 to infinity, a n minus 1, x to the n minus 1. Okay, did I shift everyone? This, all n's are n plus 2's, all n's are n plus 1's, all n's are n's minus 1's, this is minus 1 here. All n's are the same, all n's are n minus 1. So now we have to get all the indexes to be the same. This I could start from 0, there is no consequence. This I cannot start from 0 though, do you notice that? If I plug in n equals 0, it actually gives me a term. So that's not going to work. Which means that 2 is going to be the smallest index I can start at, right? So what does that mean? I have to get everyone else to catch up to 2, right? Because now just bumping this back to 0 is not going to work for us anymore. So now what we're going to do is we're going to have to start evaluating terms on all the other series to start their index off at 2. Yes?
You can't change it to 1.
1 I can change it to, that would be 0, but there's, some of these are 0, right? So my question is, could I go back to 0 to fall in line with these guys? The answer is no. Right? Because 0 will give me a term, it would actually give me a non-zero term. So what I can do is I can let these guys catch up. So here I'm going to evaluate 2 terms from here. So for the first series, I'm just writing this out so you can see what I'm doing. Plug in n equals 0, and I would have 3 times 2 times 1, a2, plus first series, n equals 1. I would end up with 3 times 3 times 2, a 3x, plus the second series, n equals 1, would give me 2 times 1 times a2, x. You would start now at n equals 2. This is just the third series. Third series I'm going to leave alone. This one, 1, 2, 3, 4. Fourth series. N equals 0 gives me a0 plus the fourth series. N equals 1 gives me a1x plus the second series actually give me a minus here, plus the fourth series, and equals 1 would give me a0x, plus, now I can start all the series from 2, all that blah blah blah, x to the n. So now this guy, I'm going to want to start grouping like terms, right? So I'm going to look for all the constants, which there are constants here. I have 6a2 plus a0. Okay, that's all the constants. Plus all the guys with x's. Here I have 18a3 minus 2a2 plus a1. Yes. Which one?
For the fourth series, why do you have too many because
First series, I had to do n equals 0 and 1. Second series, I had to do n equals 1. Third series, I didn't have to do anything. Fourth series is this guy, I had to do 0 and 1. This should be fifth. I'm talking about this one. X, okay, and that's everyone plus this huge series starting at 2, blah, blah, blah.
Can you explain that step again? Like when you took the n equals 0, n equals 1 for this series?
Yeah, I had to do it for this one. The fourth series?
Yeah. Like why did you do it?
So, because I wanted to start at 2. Right? Remember yesterday we saw that if I start a series from 0 to infinity of a(n), this is just a0 plus a1 plus a2 plus a3 plus going on. I could literally just say a0 and a1, evaluate the first two terms, and then start the series from 2. Right? To get rid of everyone here. That's what I'm doing. So if I want to start a series at a higher index, what I do is just evaluate the first few terms, and then I can start it from that higher index. So I realized here I needed to start everyone at 2, so I started evaluating terms out of the other series to get up to 2. There's a way to avoid doing this, but this is the more elementary way, so I thought I'd show you guys that first. Maybe I'll show you the other way later, because we won't get as far as I want to get in. So now, we have to set each term equal to 0, right? Because the coefficient will be 0 on both sides. So this means that 6a2 plus a0 equals 0. This means that a2, for example, would be a0 over 6. Because you want to solve for the bigger guy. So that's just a little factoid that might help us. Here I would say 18a3 minus 2a2 plus a1 plus a0 equals 0. Which means I can say a3 is just 2a2 plus minus a1 minus a0 all over 18, which I should be able to simplify that one. a2 was just a0 over 6, so this is just minus a0 over 3 minus a1 minus a0 all over 18. This would be, right, ultimately I want to find the solution, so I'm going to use these to find some of the coefficients anyway. And so,
Why you didn't times it by 2? Should be 2a2, right? It should be negative 2, right?
Negative 2a0 6's.
this is over 6,
Oh, yeah.
so I did times it by 2. Yeah, so now here I have minus 1 over 3 a0 and minus this, which is 3 over 3. So this is sort of minus 4 over 3 a0 minus a1 all over 18. So this would be what? This is minus 4a0 over 3 times 18 minus a1 over 18. I can take 2 into this goes 2 times, 2 into 18 goes 9 times, 3 9 is 27. I have minus 2a0 over 27 minus a1 over 18. Right? That gives me a3. setting this equal to 0 will actually give me the recurrence relation. I'm just going to plug in all these guys. So I have 3 n plus 3 n plus 2 n plus 1 a n plus 2 minus n plus 1 a n plus 1 plus n minus 1 a n minus 1 plus a n plus a n minus 1 equals 0. This means if I solve for n plus 2, I would have n times n plus 1 a n plus 1 minus n minus 1 a n minus n a n minus 1 plus a n all over 3 times n plus 2 times n plus 1. And that we can actually factor anything out and simplify. So this is the recurrence relation. That was a part of what we had to find. And I left off an important part of this thing. They said compute the first 4 terms. That's good for us because it means that all this work we did over here actually pays off. We don't even need this. Because this we'd only need for n greater than or equal to 2, which would give us the A4, A5, A6. But the 4th term goes up to A3, so we already know everything we need to find 4 terms. So our efforts weren't wasted there. We found the recurrence relation, that's a part of the problem. Now, solution to 4 terms is y is equal to a0 plus a1x plus a2x squared plus a3x cubed. That will be the solution to 4 terms. And we know all these guys already. So this is y is equal to a0 plus a1x plus a2 is minus a0 over 6. And A3 is minus 2 over 27, A0 minus A1 over 18. Y of 0 is equal to 6. Y prime of 0 is equal to 2. This means I can replace all A0s with 6. So here I have 6. All A1s I can replace with minus 6. All A1s I can replace with 2s. So this I'd replace with minus 6. This I'd replace with minus 6, so this is plus 12 over 27 x cubed. A1 I would replace with 2, so this is just minus 1/9 x cubed. Can we combine these guys? Yeah, 3 into this goes 4, 3 into that goes 9. So it's 4 minus 1, that's 3 over 9, so this is 1/3, right? Okay, going way back, how do we know the biggest interval to find a solution? They asked us. It was in the question. I forgot to write it the first time. They specifically asked you for 4 terms.
No, I know that they asked you for the first four, but how do you know to only use the first four when you're gonna do, when you do this part, why not equal? Like, they want you to plug in those numbers
Yes.
to get the,
4 terms just means
Like,
constant x to the first, x to the second, x to the
like,
third.
to get the first 4 terms in terms of, like, numbers instead of A naught and A1?
Right, because they gave us the initial conditions.
Okay.
Remember, the A0 and A1 are sort of like the C1 and C2 from before, right? So whenever you're given initial conditions, you're expected to plug them in. Right. So I plugged them in here and I got the first 4 terms of the series solution. So the largest interval, what we can do is we can remember what this was. This was this. Square by triangles. We did this a while back. How do we find the largest interval? We put this in standard form, remember? So this was, I forgot what section we did this in, but we definitely did it before. Probably in 3.1 or 2. Something like that. So 3 minus x. So the idea is, where this is 0, that's bad. Right? Remember, it's not an ordinary point. So x equals 3 is bad. Which means if we're on an interval, we know our initial condition is at 0. But 3 is a bad point, which means the most we can extend to is 3. Right? So radius of convergence here is going to be about 3, largest possible interval. We could actually have to converge on a smaller one, but the largest possible one would be from -3 up to 3. If we could somehow find the general term of this series, find an and make this a really nice formula, we could do the ratio test and come up with a tighter interval. But here, as far as we're concerned, the largest possible one is determined by what this is in standard form.
Jhevon, we've done it before. Don't remember from negative infinity to 0, from 0 to 3, and from 3 to infinity. Why is this one a little different?
Oh, because it is a series. Remember, a series, the interval is centered at x0. Remember when you do the ratio test, you get in absolute values, it has to go onto both sides. Right, so if it can only go forward by 3, a series would be limited to only go backwards by 3. That's why it's called a series centered at x0. It means that's the center for the radius of convergence. So it's because it's a series is why it doesn't go all the way back. That's what makes it different from what we did before. But it's similar to what we did before in this way. So go home, mull that over a little bit, and we will pick up with more series next time.